Hi, and welcome to the J Champions Conference for 2022. My name is Josh Juno, and I'll be moderating this next session. It's entitled Understanding CPU Microarchitecture, and our speaker is Alex Blewitt. Please feel free to use the chat feature to ask questions, and they'll be answered at the end of the session. With that, I'm going to hand it over to Alex. Thank you.
Thanks a lot, Josh. So hi, everyone. My name's Alex Blewitt. You're coming to the Understanding CPU Microarchitecture for Maximum Performance. And in this session, we're going to talk about what's happening inside the CPU. So how do the CPU instructions get executed? How does the data come from memory go on there? How does it get processed? And what kind of programming patterns that you can use to either get better or worse performance inside there? And we'll talk about tools that find out where you're spending your time within your CPU hotspots, what tools there are to be able to measure it, and the kind of changes that you can make to your programs to be able to make them run faster. This is a generic talk in terms of programs running on a CPU, so it applies to the JVM and just-in-time compiled code as much as it applies to C or C++ code that gets compiled. But the principles are the same in terms of organizing and processing, and you find exactly the same performance bottlenecks in Java as you would in a C++ program as well. So we're going to have a look at the performance pyramid, where you've got instructions being executed by a CPU, getting data from memory. That memory is sitting in hardware in either a laptop or a server chassis. And then you've got algorithms that process data on top of that with then system architectures and indeed distributed cloud architectures that fit together. We're going to be focusing on the top of the pyramid for this talk. There's plenty of other talks available in the J Champions conference that you can use to find out things about the lower parts of performance of the stack. And just as a quick segue, I look after the cloud at Santander UK. I'm hiring cloud people if you're interested, but that's the only commercial bit of the talk that I was going to do. So how do CPUs actually fit together and run? Most computers are built up with one or more sockets that contain the CPUs that execute your code. And you can either have a single socket in your system, perhaps with multiple cores on, which is obviously very common these days, and you can have them in pairs, or you can have them in 4-way configurations or 8-way configurations. And the more powerful machine that you buy, the more sockets that you have to be able to talk to each other. Now, those sockets connect to each other over a very fast local bus on the system, but obviously they have to be able to talk to both the devices and the memory that's connected to them. And what you can have is what's called a non-uniform memory architecture. So we have this great view both in Java and in the C level of memory just being a giant bucket that we can throw whatever we want at and it just comes back to us. But actually in the machine itself, there are banks of RAM chips that are associated with one socket. And although other sockets can see them, if you had to go from one side to another, there's delays that come inside the transfers for that. And realizing that this happens and learning to configure and deal with non-uniform memory architecture means that you can actually pin some resources or some programs to run on a particular corner of your machine to optimize performance on there. If we actually then drill down into one of these chips in there, what do we get inside? Well, inside these chips, we have a bunch of different cores, and the cores are actually the processing units. In the olden days, when you had a 286 or a 386, the core would be the same as the socket. There'd only be one inside there. But we've gone multi-core for quite a while now. In Broadwell, the cores communicated using a ring bus. So as well as the socket communicating to other sockets, there's another networking channel inside the socket itself that connects the output from one core into the output of another core. And this was organized as a bidirectional ring bus, both to be able to talk to memory and also to be able to talk to devices via PCI. There were different extensions for that. There was an 18-core die, which added another column of sockets down the right-hand side, and that had half a ring for it. And indeed, the 24 version had 2 rings running parallel inside there. There was then special shunting mechanisms which allowed you to move data from the left ring to the right ring, essentially when they wanted to be able to communicate with each other. Now, clearly, if you've got a core on the very left-hand side of the CPU, and it's communicating with a core on the very right-hand side, even though it's the same die, you'll end up having to go through a few jumps to be able to get there. So not all core-to-core communication is the same. For Cascade and Skylake, they changed the model slightly, and instead of having 1 or 2 rings with punts between them, they then organized them into vertical channels and horizontal channels. And they were both bidirectional rings as well, but it meant that if you wanted to go from one core to another core, you could then go along and then down or across and then up. Very much like Milton Keynes, which is where I live, except we have more roundabouts. There were then 18 core packages on there and 28 core packages that built up the same thing. But each one of the light green boxes here is its own core. So it's got the all of the execution units that you need inside there. And then they talk via the buses, via the memory home agents, to be able to communicate and pass data between different cores, and also to send requests to the memory controllers. And in this case, we've got a dark gray memory controller on the left-hand side of the chip with a few DDR4 banks, and then on the right-hand side, the same thing with those DDR banks as well. So if a core in the middle wants to make a request for memory, it has to send a message to the memory controller on one or either side of the box. That then has to send the request out, and then it gets the data back again. Now, they also built a 56 core die of this, and you can configure these in what are called sub-NUMA clusters. So because within Skylake, you've got one memory controller out the left-hand side and another controller out the right-hand side, then you could split them into two NUMA clusters and effectively treat them as if they were two separate processors. That can be useful sometimes, because then you can pin your program to run effectively on the left-hand side of the machine and perhaps get better cache utilization. The 56 core die was actually just two of these dropped into a single package. And so they still had the same communications, they still had the same way of communicating out with things, but they would just put two dies together and then package it up within one unit. So you'd end up with a 56 core machine inside there. The next evolution of Cascades and Skylakes were called Ice Lake. And Ice Lake was something that essentially improved the cores that are used underneath. So Intel talks about the packages, the marketing names for these processes, but it also talks about the core. Things like Sunny Cove, Golden Cove, Willow Cove are the cores that execute in those little boxes inside. And they were up on the Ice Lake cores in terms of what they were building. There's a 28 core they have for that in the server one. You can also get a 40 core one, which throws much more cores on the local machine. But each one of those kind of dark green boxes is the core inside there. The purple boxes are then the communication agents that allow you to then communicate with the rest of the chip. And then around the outside are the interconnects which you have for being able to talk to different devices. So the PCI interconnects for being able to talk to devices like hard drives or solid state drives or non-volatile memory. And then you've got the UPI, which is their interconnect, which they use to connect up to other cores when it's running in a multi-socket system. Following from that, there's Alder Lake, and Alder Lake is the next evolution on from there, but at the moment it's only available in client packages. They did talk about the at CES a week ago, 2 weeks ago, they talked about what they were bringing out in terms of Sapphire Rapids, which is going to be their successor for the server cores, and they're going to be built on Willow and Golden Cove as well. The interesting thing about Intel's transition into Alder Lake is this is the first time where they are building a non-uniform core package, in the sense that they are having performance cores and efficiency cores. Now, ARM has been doing this for a while with Big Little. I'm sure that the other processor vendors have also been doing similar things, but Alder Lake is the first time we're seeing this split of cores that are going to be available first for mobile devices and then for server devices as well. Quite how well the Big Little approach works on the server side, I think, will remain to be seen. And there are certainly plans for some of the Sapphire Rapids to have purely Golden Cove, the performance cores on there, rather than the efficiency cores on there. But the other thing to note is the efficiency cores only have a single thread of execution, whereas the power cores have two hyperthreads running next to each other. Where the hyperthreads continue to be an interesting thing because of various different performance issues like Spectre and Meltdown, which we had a few years ago. I don't know, but certainly it's possible that we'll see some of those being used. And so the thing is, when the CPU is talking, it needs to be able to get its data from somewhere. And pulling things from memory is incredibly slow. So we have cache that makes the memory more local to it. You might see it annotated by a $, which is a pun on the word cache, obviously. And this information we've compiled here is for the Sunny Cove cores in Ice Lake. So there's a register file, which is where registers store their data. They're like local variables for CPU. And although the instruction set may only have 10 or 20 or 30 different register variables that you can use in the ISA, that is in the instruction set, actually CPUs have a much bigger register file underneath. And so when your program is talking about loading from the A register or storing into the B register, that could be mapped into any one of 120 registers if they're integers, or 224 if they're floating point values. And this allows the core to execute out of order and be able to do more processing. accessing something from a register file takes about 1 clock cycle. Pulling it from the level 1 cache takes about 5. It used to be 4 in the previous generation. They slowed it down to 5 because presumably they've got more caching and checking inside there. Alder Lake and Golden Cove are going to bring that down to 4 again. And the level 1 cache is actually split into 2 things. It's split into the data cache and the instruction cache. And that's because you typically want to operate on 2 streams of things separately, right? Your program is always going to be running instructions. You'll always need instructions in the cache, particularly if you're doing loops over very small blocks. And then you'll need to be processing data, which is going to be a completely different part of memory. So they're split into 2 things. For Sunny Cove, we've got 48K's worth of data in the level 1 data cache, and we've got 32K worth of level 1 instructions on the instruction cache, and that's per core. So if you've got 20 cores, then you just multiply all those numbers by 20. Those two share a level 2 cache, and the level 2 cache is shared between the data and the instruction, but it's core local. So in this case, Sunny Cove has a 512K cache, which takes, again, about double the time from the level 1 data, just over double the time to be able to get access from there. And as you go further down the memory hierarchy to the level 3 cache, or the last level cache as it's sometimes known, you then go up not quite an order of magnitude, but certainly an order of magnitude from the last level cache to the level 1 cache. The last level cache, the level 3 cache in the server cores that we had actually are distributed around the cores themselves. So in effect, it's like a buffer that will overflow and be able to be shared by anyone. So core A on a die is going to have a slice of that 1.5 meg, and then core B on that die is going to have a different slice of that 1.5 meg, but both cores can see content in the level 3 cache in both places. And then if you're accessing RAM access time is then another order of magnitude bigger than that, or at least a small multiple of that. And it does depend on where you're accessing it. If you're on a CPU, which is connected to the memory bank that you're pulling it from, then it's going to be accessed quite quickly. If it's on a further away slot and it has to jump over to get to the other side, then it's going to take longer. And if you're running in a multi-socket system and then you have to pop out of the socket and then transition to another socket to be able to get your memory, then it can be even longer still. And so that's one of the things that I think you really need to take away from this, that not all memory accesses are equal within a program. And just because you can reach to any memory location doesn't mean that they're all going to be the same speed. Now, this was summarized very well in what was called the beer cache hierarchy by Michael Heinrich in 2014, and I think popularized by Holly Cummins, who then tweeted out about it. The idea is that you've got different levels of access that you can be able to pull inside here, from the register at the top level through down to memory, networking, disk, tape, and so on. And a register is like having beer in the mouth. So take a swig, and that's inside there. Level 1 cache is like beer in the hand, so it's easy enough to be able to get to. Level 2 is where you've got beer in the ice bucket just down on the floor there. If you are using the last level cache, or level 3, that's kind of like walking to the fridge to be able to get another beer. Main memory is like going to the local store, the one down at the end of your road, to be able to get a new beer. Getting it from an SSD is where you're driving it out to a store, maybe not in the local region, but in the same town as you. Accessing things over the network, kind of like flying to another country to be able to get your beer. And if you go further than that, magnetic disk is like you're actually still waiting for the beer to be brewed. And if you're coming off tape, then, well, frankly, you've just planted the beer in the first place. That gives you an idea of the different levels of access that you have in different parts of your system. And getting data from disk, or getting data from even from a network on a remote host, can actually be a significant amount of time as far as the microprocessor is concerned. You can have a look and find out what your machine looks like by running lstopo. And lstopo will give you a view that looks like this. It shows you how your package is broken down on your machine and what the different memory cores are inside there. This was run on the laptop that I'm using to demonstrate this. It's a single socket system, so there's a single package inside there. We've then got a couple of different levels of shared cache. In this case, we've got an L4 cache. That's the GPU memory for my particular machine. And then for each core that we have in there, we've got the level 2 cache and the level 1 data and level 1 instruction that is then split between them. And inside each core, we've then got processing units. And those processing units are effectively hyperthreads. Hyperthreads work by being able to reuse some of the components inside the CPU when we're waiting for some of that data to come back from memory and you're otherwise blocked. By the way, if you want to know how memory works, there's this great picture that was created for the .NET OS organization. They've got an anatomy of how a single bit is stored within a single capacitor inside the cell, which is then built up into arrays, banks, DRAM chips, and how that communication goes off. So that's in there. And I will be making these presentation slides available so you don't have to quickly copy down or rewind the video to be able to get to these links. So going back to our memory and cache thing, that's not the only kind of cache that you have within a CPU, although it's the one that I guess some of you will be familiar with already. There's another type of cache called a TLB, or translation look-aside buffer. What the translation look-aside buffer does is it allows you to translate virtual memory addresses into physical memory addresses. In other words, physical RAM chips that are running inside your machine. The way that that works is whenever you do a lookup, the topmost parts of your virtual address are indexed into a table, which then says, and you can find this at this physical location on your machine. And that's one of the things that a multi-processing OS will do for you. The lower parts of the address are actually just copied the same through. So it's only the top part of it that's doing the mapping. But because this happens every time you look up an address, including instruction pointers or being able to load data from memory, this needs to happen quickly. So the translation look-aside buffer is there to be able to store mappings of programs that are currently running. If it doesn't find a mapping inside there for an address that it needs to look, it then needs to call into the operating system, and the operating system needs to figure out which page to flush and then how to bring in a new page inside there. And again, this is split into data and instruction TLBs, and both of those have a shared TLB that they can bring content back into. Couple of things on this. If you've got the PCID extensions, which most modern processors do, a few years ago it wasn't necessarily the case, then you can actually get faster flushing when your processes swap out or terminate, because each virtual and physical mapping is then associated with a PCID, kind of like the process identifier on Unix, but maybe a little bit more granular. And that allows you to evict mappings for a single program rather than having to flush things for all programs at once. And that's useful when it comes to being able to deal with the Spectre and Meltdown type mitigations, because one of the mitigations in there is just to flush all of these content out so that they're not available. So how do the memory pages actually work in practice? Well, we've got two processes here. They've got the same virtual memory address of 80001234, and they point to a page in memory. As far as the programs are concerned, they're looking at the same address, but actually they're backed by a different physical page, and that mapping is then stored in the TLB. The other thing that the TLB allows you to do is to share some pages. So you can either have some programs sharing read-write memory and use that to be able to pass in as a communication buffer, or you can share some libraries that are loaded or some kernel interfaces that are loaded, which are read-only in both places. And that's the general concept of a page. Here we're showing that there's a two-layer page structure. In actual fact, when the 86, 64-bit processors came around, they had a 4-level page structure by default, and the isolate processors then extended that to a 5-level memory page, which gives you 57 bits worth of paging inside. So what about the page sizes then? Well, the page sizes can either be 4K, which was the original one back when the 386, when this first started being used, or it can be a 2 megabyte size, or it can be a 1 gigabyte size. And your POC CPU info will then tell you what support you have for being able to enable those different HugePages as well. Why would you want to enable HugePages? Well, realistically, 4K, which is the default size, is not even enough to store the picture of the screen that you're staring at the moment. Right, so this screen, if you took a screenshot of it, it would take up many 4K pages in memory. And that can be quite wasteful, because then you are polluting the data cache or the data TLB cache with a lot of mappings that perhaps aren't necessary. If you have it as a 2 megabyte size, well, maybe you only need one page for that now. And that can obviously improve the locality of the data, and it also can improve the mapping when you look it up. However, if you're working on a JVM and you're working in multi-gigabyte heaps, then actually it might make sense to have a gigabyte as being the page size. Certainly if you're writing very large processes or pages, then effectively, if you had a 1 gigabyte page and a 8 gigabyte JVM limit, then you'd only need 8 pages of memory, and that would probably, the TLBs will be in memory all the time for that. The problem is they're not easy to configure. So you can use something called HugeTableFS, and what that will do is when the Linux kernel boots, it will reserve a subset of memory to be put into huge page sizes, and you can then specify which size you want to use for those huge pages afterwards. Problem is, you kind of need to know ahead of time what you're going to use them for. And if you don't know, then you don't know how much of your memory to reserve for HugePages, then it can be a little bit of a problem. It also requires root or suitably permissioned apps to use HugePages, which is probably a reason not to use it more than anything else. You don't really want processes to be running as root unless you can help it. So there's something called transparent HugePages. And what transparent HugePages does is it doesn't need you to do anything specific. It doesn't need the CPU or boot time to be configured in a particular way. All that happens is when your program runs, behind the scenes, the kernel will try and create HugePages for you and then give you those HugePages to be able to use. Now, the default page size is still 4K because, frankly, there's a lot of mallocs going around the place. And if you just want to hold the string "hello world," you don't need a whole 1 gig's worth of space to be able to do that. But programs can then advise whether they want to use large pages or not. So things like the JVM can decide that it wants to use large pages for being able to store the Java heap or for some of the native memory tracking. And it allows applications to opt in. So it's not an either or case, it's an opt-in on demand. You can configure this on the Linux kernel by writing a value to the transparent HugePages enable setting. If you use madvise, then it will say, okay, give everyone a small page unless they specifically ask for a bigger one, in which case please ask nicely on that. The only downside with using madvise for being able to do this one is if your program requests a large page and there isn't one available, then it will delay trying to find it and trying to coalesce and effectively defrag memory before it gives you that back. Sometimes that might be useful if what you're doing is you're rebooting your server machine on a Sunday evening and you want to make sure that everything's there. But actually, if you're wanting to be able to recover quickly, you don't really want to hang around for that to happen. So you can write a defer flag to the transparent HugePage defrag. And what will happen then is if you ask for a huge page, but there's nothing available, you'll just get a bunch of small pages instead. And behind the scenes, the kernel will then try and coalesce them into a huge page and then swap it out for a huge page later if you want. So that would be the advice of if you wanted to set those up on Linux for your large Java programs. Now, when you're loading data, we think of data as being byte addressable so that we can just read a byte at a time. Actually, under the covers, we read a cache line at a time. And a cache line for 64-bit systems is typically 64 bytes, sorry. But in fact, some of the Apple ARM processors use 128 bytes now for being able to store their cache line size. And it wouldn't surprise me if we see similar things happening with future Intel or ARM or other processors that run in there. So even if you're reading and writing a single byte, even if you're writing a single Boolean value into memory, you're actually causing a 64 bytes worth of memory to be able, or 128 bytes to be able to go backwards and forth. And the cache line is annotated to say whether or not you've written something locally or whether it's just a read-only copy. If you have a read-only copy, it's shared, then if you need to evict it to make space, you don't care, you just throw it away. If you want to modify it, then it's in one of the other me modes. So it's either exclusively owned by the core, but it's not modified yet, or it's modified and you've got data that needs to be flushed. The reason these states exist are so that cores that are running on a different part of the die, or indeed on a different socket, can communicate and say, I own this piece of memory. And if you want to do it, you have to take the version of memory that I'm using and then flush that back into some shared last level cache before you then start doing manipulations on it. And this is important when you talk about being able to do with locking algorithms, because you need to make sure that that's there. Volatile will make sure that you've got your data flushed back to the memory. If you don't, you can end up with some weird conditions. And that's one of the reasons why Java is particularly good, because it's got a very strong memory model and it says how they map to different memory transitions that happen under the covers. There's various extensions to Messi. There's a link to Wikipedia. You can read up more about that if you wanted to. One of the other things that the CPU will do is as you are loading data from memory, it will try and get ahead of you and get memory that it thinks that you need. So if you've got a linear array and you're just doing a scan through all of it, then the CPU will notice and then start bringing in adjacent cache lines for you to be able to load. Now, obviously, it's not going to do it just after the first one or two, but under some kind of specific mechanism, the CPU will notice that it's happening and it will be able to bring you in. Same thing also happens if you're reading, say, every 8th byte or every 10th byte from a memory area as well. So it will then read in those cache lines. And the read-ahead caching side of this is actually pretty good. Whether you'll be able to see that and used from a JVM, probably not, because actually by the time you get to the JVM, the memory level and the way that you're streaming through data isn't going to have that much visibility. But actually structuring your data and being able to pivot it so that you read and you lay it out in memory in an appropriate way can be a good way of speeding up programs. If you're in the C world, there is a C built-in which you can use built-in prefetch to say, I know I'm going to be needing this ahead of time. Please make it available. However, experience has generally shown that people trying to prefetch their content from a further memory location don't actually know what they need to do in order to be able to get that presented and loaded into memory. So only use that if you are actually measuring and you can prove a measurable benefit. And bear in mind that that measurable benefit may disappear either due to other things on the system also thrashing, or it may be that your program changes after you originally add that and now it's no longer valuable. The thing that you can tell in Java is something called false sharing. False sharing happens when you've got two cores trying to modify bytes in the same cache line. And it doesn't actually matter whether they are the same byte or whether they are within the distance of the cache line itself. But if you're reading and writing a byte from the beginning of a string or the end of a string, and the string will fit into a single cache line, and two threads are repeatedly, for example, updating, incrementing values or decrementing values inside there, the first thread is going to try and obtain exclusive ownership of the cache line. The second thread will try and do the same. Then they'll have an argument over messy, and it does get messy under the covers. The way that you can avoid this is by padding out cache line sizes, or maybe double the cache line size between things. There is a JDK internal cache line size that's used in the Java lang thread class as a padding mechanism to allow threads to not collide when they're reading and writing the value. But that's an internal JDK thing, and it's not visible to external users, although there's nothing stopping you doing padding if you wanted to. However, be careful with just building up a class and sticking in bytes before and afterwards in the source file, because the compiler can decide to arbitrarily reorder those bytes within there when it comes to memory, particularly in order to get finer grain layout. And there used to be a quotes hack where you could have a superclass having one set of fields which would be at the front, then a subclass which would be in the middle, and then another subclass of that which would then be at the end. And that's what JMH used for a while. However, and that was because Hotspot didn't intermingle. It didn't use free spaces in the parent class if it could do. That's been changed, I think, if not in JDK 17, then maybe JDK 18, so that trick no longer works. But as with all things performance-wise, you do need to measure it and find out if it's actually what you want to be able to do, rather than just assuming it is. So for strategies for making better use of your memory, make sure that your data fits in the cache size. Obviously, it's great if it fits in L1, if not L2, then if not L3. Stride through the data in a single pass. Whilst it's called random access memory, random access is going to pull a lot of things out. So processing data in a single pass is more efficient. Depending on how you've laid your data out, you might want to have a structure of arrays instead of array of structs, because if you store a bunch of points with XY coordinates in a single class, then you'll end up with quite a lot of wasted space. If you have an array of X coordinates and an array of Y coordinates, then you can stream through those very quickly. And look out for multi-threaded or contended writes. Try and avoid those ones if you can. You generally want to try and find thread local or CPU local accumulators if you're doing lots of processing, and then bring them together in a final merge step, because that will be a quicker way of handling things. And lastly, on compression, if you have compressed data, even though it can take a while to uncompress, the amount of benefit you get from loading this from disk versus the time it takes the CPU to actually execute the decompression algorithm means that decompression on the fly is quite a good advantage for a performance benefit, simply because there's then less memory traffic that comes through, there's less disk traffic that gets executed, there's less delays when it comes to be able to load those things. And that's why you find compressed file systems can often be faster than an uncompressed filing system. And it seems strange that you're adding more work to get a speed up, but it's purely to do with the fact that the CPU can work a lot faster than the disk can. The other strategy is for being able to pin memory and threads. If you want to have your processes running, then a great pattern is to have a single threaded application pinned to one core and another single threaded application pinned to another core, and then communicate over some kind of shared mechanism that you control, because realistically, that's what's happening under the covers anyway. You can isolate CPUs to stop the CPU running kernel threads on there to make sure that you have a limited amount of jitter. You can use CPU sets to say what CPUs you want to allocate to particular tasks. Task set allows you to say, I want to run this process on this core or this set of cores. There's a NUMA control which you can use to be able to clamp memory for a particular process down to one particular side of the bank. And there was at one point use NUMA on the Java runtime, but I can't remember if they took it out or if they enabled it by default. I seem to recall something's happened, but I don't have the data to hand on that right now. So we talked a lot about memory then. Let's go a little bit deeper. We're getting data to and from memory, but for what purpose? And the answer is because we want to execute it on the CPU core. So we talked about the instruction cache and the data cache which we're pulling in. Those are instructions that are being pulled in. The front end's job is to be able to pull in data from memory, from the instruction core, and then translate it into micro operations or micro ops to then hand to the back end, which is then going to execute that those micro ops. It's almost like an extra translation there, like you might have in a program that is translating from Java code into native x64 instruction set. So inside the front end, the whole job for this is to be able to decode what gets thrown at it, figure out what you mean, and then pass them onto the back end in a way that's suitable for executing. So we've got a bunch of data that's coming in from main memory here, arbitrary bytes, don't really know what they're in. The first part of the step in an Intel system is to pre-decode it and figure out how long each instruction is. One of the downsides of the Intel instruction architecture is because it is variable length, you can't say this instruction starts here and ends there. And one of the advantages that ARM has generally over x86 is that it has a fixed width instruction architecture, so you've always got a good idea of where the next instruction starts. But for Intel, it has to guess that. And in fact, there's a dedicated part of the pipeline whose sole job it is to guess where the instruction boundaries are for this. So once it's split that up into different instructions, those instructions are then assembled into operations. In this case, we're pushing some data to the buffer pointer. We're moving something from the buffer to the stack, and then we're incrementing a byte in memory location 4D2. And possibly some other junk which it doesn't know about. It'll get that round next time. So let's just focus on one of those instructions, incrementing a memory location. Now that's a single instruction in x84. It's kind of like x plus equals 42, for example. But inside the CPU, that's got to be split into 3 micro operations. And the 3 micro operations do a load from that memory location to increment that variable, and then to write that memory location back again. And generally, one instruction is going to map to one or more micro operations. You can have it the other way around. You can have 2 instructions being mapped into a single micro operation, but it's more rare for that to happen. And indeed, some instructions just map to a single micro operation under the covers. Now, there's various different caches and processes that go on inside here, because once you've done a decode of an instruction once, you know what it looks like, and there's a specific micro-op cache that's used to be able to hold some of these things inside. That's then used by other processing things like the loop decoder and the branch instruction decoder. When you've got a loop, especially if it's a tight loop and you want to jump back to a memory location again, if you've already decoded this loop once and enough of that decode still lives in memory, then you don't need to reach out to main memory or indeed the level 1 instruction cache to be able to get your data from that again. So the micro-op cache allows you to serve content inside there, and there's a specific thing called the loop stream decoder, which will allow you to serve content directly from there. There's also a branch predictor as well, and it's worth diving into a little bit what the branch predictor is all about. What happens when you have a comparison operation followed by a jump is that your program is going to suddenly jump to a completely different part of memory and be able to execute those instructions from the get-go. Mostly it's correct. The branch predictions have got better over time, and 95%, 99% is kind of the accuracy that you might expect for the branch predictor in a usual run-of-the-mill program. And one of the advantages that Intel and others make as they go from iteration to iteration is improving things like the size of the micro-op cache that you're using, or the branch prediction algorithms that are being used in place. And what the CPU will do is it will learn patterns based on your behavior. So the branch prediction is, say, if you've got this operation, are we going to take the branch, yes or no? Because if we are going to take the branch, then we will take the instructions as if we had done and just hope we are correct. And if not, we'll then back out and go to the other path instead. You can actually see this exposed at the Java level. If you iterate through a random set of numbers and you have a loop that says if it's bigger than a threshold or lower than a threshold, then take different actions, you will find a different performance profile if you have a set of random numbers versus if you have a set of completely sorted numbers. Because if you have sorted numbers, the first half you're always going to be taking the left branch, and then the second half you're always going to be taking the right branch. And that will be noticeable and measurable even at the Java layer, even if it doesn't use the even if it doesn't seem obvious why that would happen. This is also one of the reasons why unrolled loops and inlining is a performance benefit. You probably shouldn't do manual inlining yourself. You should let the compiler or the JIT do this for you. There are certainly some patterns that will make it more amenable to being to do JITs, but the whole point of doing inlining is that you remove a branch, and the whole point of doing loop unrolling is that instead of jumping back every time, you maybe jump back every 5th time or every 10th time. Now, as well as the branch predictor stats that get calculated, there's also something called the branch target predictor. And the branch target predictor says, if you are jumping to a location of a variable that you don't know at this point, where are we going to go? Well, logically, it could go to anywhere in memory, but actually, if you hit this one a few times, you probably are going to hit the same thing. And this is, of course, used a lot in Java and in other OO type systems where you're taking the address of the object, you're then looking into the object to find out what class it is, you're then going into that class to find out the method instruction, and then you are jumping to that method instruction. So many object-oriented programs will suffer from this kind of we don't know where the jump is encoded specifically. Although in the case of the JVM, if it notices that the type of class that you're always doing is a known one, then it can switch to using a direct implementation and be able to jump to that directly, which is one of the ways that the JIT gets performance. If you're interested in knowing more, Dan Liu has got a great write-up on branch predictors. It's a few years old at this point, but it does go into it in a whole bunch of detail. And the reason why all of this matters is because we have pipeline stalls. Pipelines are the way that the CPU processes things bit by bit. Most CPUs are quite deep, 15 to 20. They're probably not as bad as they were in the Pentium type days and as the end of the Pentium line ran out, because we just got more and more stages and the pipeline stalls got more and more expensive. But I think for the Ice Lake, it's about 19, between 14 and 19 stages. But each different iteration is going to have a slightly different length of thing inside there. And the point is that when the program counter changes because you've jumped somewhere, it causes a flush of what's happening inside the pipelines. You need to throw away all of the work that you've been doing, and you need to start again from the beginning. Hyperthreading, if you have it, can take advantage of some empty slots inside there. Sometimes that's beneficial when you have these sorts of stalls. Sometimes it's not. It does depend on what your processor is doing. So here's a quick example of how it might look like with time going to the right and the new instructions coming in from top to bottom. So the first instruction we bring in goes through a fetch. That's bringing it from memory. The first instruction, the blue one, then goes through a decode cycle while the CPU is then fetching the next location from memory. And then once the blue instruction has been decoded, it's executed, and the green one starts being decoded, and then we fetch a third instruction from memory. It turns out this one's going to be a jump. We don't know that yet, but it'll cause problems for us. And then finally, you've got the write back of the instruction when it gets executed. So that's, updating memory locations, flushing them out to the backend cores, and so on. And whilst the first blue instruction is writing and completing its operation, the second green instruction is still going through its execute phase. The jump instruction is just being decoded, and then the next instruction, and we've got the orange instruction that's coming in, is just being fetched from memory. And then the green one goes to the right, jump instruction starts executing, and here's where the problems occur, because the jump instruction in the red X that we've got means that actually the work that we've done with the orange and pink colors are completely useless. Their results are just going to get thrown away. And there's no write back for a jump instruction anyway. So what happens is you have a bubble or you have a pause inside there whilst the fetch instruction process is given a new location in memory to start pulling things from. And so that's the stall that we have, or the pipeline bubble that goes on. And we lose a bunch of execution time shown here by the kind of hashed values that don't get brought in. The thing that this notes is I've sort of indicated it's almost instantaneous from when you do the jump to when the fetch instructions start coming in, but there actually may be a couple of other bubbles inside there, and all of the work that you've been doing in flight is therefore ready to be ditched as well. And this is just showing a 4-level pipeline stall. As I said, for the modern CPUs, they have up to 20 pipeline stages, and so there's much more work that gets wasted each time you do a jump to an incorrect location or to which the branch predictor gets the answer wrong. So what does the execute and write back look like? Well, the front end is doing the fetch and decode in this instance, and the execute and write back is being done in the back end. So we pick up from where we had decoded our increment operation into a load, increment, and store op. That gets put into the back end, which then goes to a scheduler and be able to map the content. Now, I mentioned previously that in the instruction level set, you had the A register, the B register, the C register, and so on. That gets mapped in an allocation stage to some of the register entries in the register files. So we've got 280 integer registers that we could use. We've just picked 99 for here. And what happens as it comes into the allocate stage is that we are rewriting the variables that we happen to be using for the register 99 in this case. So there's no real relationship between the register name that's used inside the backend versus the instruction set that gets passed in. But when you get passed in instructions that have a data dependency, then they always get mapped to the same one. If you have 2 instructions that come in that don't have a data dependency between them, even though they may happen to be using the same register name for their storage, they may get allocated different registers in the backend. And those then get scheduled on what are called ports. And so in the core, you have different ports. There's 9 of them or 10 of them. In Ice Lake, I think the Alder Lake Golden Cove gets that up to 15 ports or something. But I haven't seen the detailed instructions of that just yet because we haven't had them yet. And each one of those ports is like a very dedicated, specific thing that it can do. So all of the ports can do arithmetic and logical things, comparing, processing, and so on. Some of them have got the ability to do shifts, some of them got ability to do multiplies, some of them got ability to do divides, and so on. The LEA is the load effective address. Load effective address is kind of like a separate arithmetic unit that's a byproduct of the x86 instruction set architecture. So you can do a calculation of multiply by a small power of 2 and then add an offset in an LEA instruction that otherwise you'd use either an ALU or 2 ALU operations for. So these then get mapped to ports, and effectively each port has got an incoming queue of requests. And the idea of the scheduler is that it's trying to keep all of the ports as busy as possible at all times. So in this case, the load gets sent to ports 2 and 3, which are doing the load generation, and the stores go to 4 and 5. So the first thing we do inside here is we're loading register 99 from the contents of this memory location. Turns out that value happens to be 2A, and that's then stored in the register file. Now, as soon as that's updated in the register file, things that are depending on that register can then kick off. So in this case, we're doing an increment R99. That will then update it in memory, and once that's been done, we then unblock the write back. So this turns into 2B, and then it gets sent out the store buffer to the data cache, and then subsequently back to main memory. Each core has got a slightly different arrangement of some of these things, although they're usually extensions of the previous generation rather than a big change. And the thing that both the load and store use is an address generation unit. So those address generation units are consumed as part of figuring out what the address is to read from or to write to. Ports 8 and 9 to allow additional stores were added in the Ice Lake cores, and it wouldn't surprise me if we see more load ports and more store ports being added within the new Golden Cove and Willow Cove, and we might even see some new integer and floating point units as well. If you want to know what the size of each of these ports are or how they work, you can find a bunch of microarchitecture diagrams. There's a Twitter user called Cardiac who has been building up a large number of these different microarchitecture diagrams with the different states in there. You might not be able to read these. I certainly can't. There is a Google Drive link at the bottom of it, but Cardiac posts these on Twitter as well, so you can go to his or her Twitter profile and be able to find that out. So we talked about being able to get stuff into and out of the CPU. How do we know actually what's going on inside it? How do we figure out what ports are being used? And the way that we can use this is by pulling a utility called Perf, because each CPU has got what is called performance counters. And those performance counters are kind of like an I variable that just gets incremented each time you do a cache miss, or you do a TLB miss, or you do a branch prediction wrong, and so on. When you run Linux Perf, it will interpret the arguments that you pass into it and be able to configure the performance counters within the CPU to be able to give you the results that come. You can run perf record, which will run a program, generate some data, put it into an output file, and then you can generate a report or annotate, or be able to record performance counters for a single thing. This is actually very useful because it's used by tools like JMH and Async Profiler. And what JMH will allow you to do is to run your Java program and be able to collect performance statistics of the thing under test. If you're not aware of JMH, then you can look at it. It's an open JDK project run by Alexei Shipilev. And there's Perf, which will give you the Perf data. There's Perf norm, which normalizes them to a kind of 100% value. And then there's Perf ASM, which is like the ASM processor for the JIT, but it will tell you in which instruction you spent most of your time in and most of your calculation in. And that's sometimes good for finding out where the performance issues are within your program. Async Profiler also has support for Perf as well. What the support it has for Perf is that if you use the Perf map agent, it will talk to the JVM, and as it's generating and regenerating native code, it will write out a Perf map. That Perf map can then be processed and integrated into Perf operations to then give you an idea of where the native operations and the native JIT things are taking some time. And in actual fact, the Async Profiler has an ability to measure both the Java interpreted and the JIT compiled code and give you a very good flame graph report inside there. That's in a GitHub organization called JVM Profiling Tools that you should find out about. So Perf record is what these are using under the covers, or the APIs that this uses under the covers. When you record what's going on, it samples the process counter, and the more it samples, the more accurate you get, and you have then a good idea of how much time you spend in each location. It's worth noting that Perf isn't always going to give you an accurate value, because by the time you've calculated your position, the program counter may have moved on. So you get what's called event skew. An event skew might mean, if you are spending all of your time in an instruction that is zeroing a register, that's probably not where the time is really being spent. It's probably something that's one or two instructions above it, and it's spending more time. And you can increase the accuracy of the performance thing by adding a :p on the performance counter to increase the precision of that particular counter that you're looking at. You can also use it to capture branches. If you do perf record B, then -B, then it will tell you which branches you get taken. So it really only measures the branch points in your code. But you can then generate a call graph from this, which actually then looks interesting to show you how your program's actually running at runtime. And if all you want to do is capture which branches run, then Intel processors have something called the LBR, which is it's a special mapping for the last branch record taken. So every time you take a branch, the processor writes that entry of which branch was taken into a kind of rolling log, and then periodically it flushes that out to the perf caller, which will then give you an idea of where your program is spending its time, but also the hot loops in your program as well. And you can also enable Intel tracing as well with that. There's a couple of LWN articles under there which talk a little bit about how you use those things. But under the covers, what Perf is doing is it's reading counter stats from the VM. Now, there's a lot of different types of things that you can count. So the number of task clocks that are being taken, the number of page faults your program has done for being able to pull pages in because you ran out of virtual memory space, the number of cycles that it took to execute, the number of stalled front-end cycles or instructions that you have, or branches or branch misses that you use to be able to calculate things. So there's a bunch of default things that you have with the counter stats that are there for free. Some of the other ones that you want, though, are not enabled all the time. They're only enabled when you flip the bit to be able to record those particular performance counters. And the CPU, when you enable the performance counters, if you don't have enough spare counters, you can then multiplex or kind of swap backwards and forwards between recording event A type and recording event B type. And if you split them equally between the amount of time you do the measurement, then you get some kind of overview of what's happening. The interesting thing to look for is the number of instructions per cycle, or IPC, also sometimes CPI, which is just the inverse of it. And if you get an IPC of 4 or greater, you're doing pretty well, because most of the modern stack of machines will be able to retire 4 instructions in one go. The older late ones, I think, can go to 5 or even 6 instructions in one go, so those can go up a little bit. If it's much less than 1, then there's performance on the table that you can take. If it's 2 or 3, you probably wouldn't want to do this unless it was a particularly heavy program that you were using. So the performance counters, you can read some standard ones like instruction cycles and branches. The programmable counters you can set to specific things. So you can actually measure the amount of TLB load misses on the instruction cache, or the last level code load misses, number of UOPs dispatched to port 5, which was one of the ALU ones that we talked about. And if you don't have the specific name for them, you can then pass in the event code, which you can find from Intel's instruction guides, or you can have a look on some of the documented websites that talk about them. But mostly it's easier to use a tool. And Ahmed Yassin created the top-down microarchitecture analysis, or TMAA, which is essentially a way of saying, okay, where's the program delayed? Is it delayed on the front end, or is it delayed on the back end? And if it's delayed on the front end, is it to do with the bandwidth that you get pulling in, or is it to do with the parsing, or is it to do with the memory misses? And if it's on the back end, is it because you're trying to do too many floating point instructions and you've only got one floating point instruction to be able to deal with, and so on. And this microarchitecture method really starts off with, have you allocated a UOP? In other words, have you ever gone to the back end? If you've gone to the back end, then does it retire? In which case, that's fine, that's good, that's where you want most of the things to be. If it doesn't retire, that's due to bad speculation. Maybe there's things that you can do to be able to deal with that. And if it isn't ever allocated, it never makes it out of the front end, then is that because the back end stalled, or we've got some problems on there? So it might be the back end is bound, or it might be the front end is bound. So you can run the tools that are there, or you can have a look at anti-clean's repository, or you can use perfstat top-down. And what top-down will give you is then an overview of your whole process, your whole machine, to find out where it's doing things. And it gives you an idea of where things are retiring, so that's good, where you're being held up with the back end, where you're being held up with the front end, and bad speculation things. So what's interesting is, even though the CPU might be reporting 100% utilization, actually only 15% of that CPU is being used. And so that's an opportunity that you have to be able to increase the throughput of your program by noticing where you can fix these problems. So Andy Clean's has got a repository on the PMU tools, which you can find out, and he's written a manual on how to be able to do this. And you can then drill down in different levels. So you can run at L1 to be able to see levels at the first level, and then you can step down to level 2 and level 3, and it will give you an idea of what's going on. So in this case, I'm running a single thread with not multiplexing counters, and I'm just running base 64 on temp round to give some load to go on. And this is the first part of running this is we're back-end bound. You run it at a lower level, we're back-end bound on the core. Run it at the third level, and it turns out it's ports utilization. So actually, if you're running out of ports, your only option is to buy the next generation of CPU, because it's not really going to affect it. Or you might be able to optimize your algorithm, or you might be able to do something like switching to using AVX or something to be able to do SIMD operations on it instead. One other thing that can have some interesting consequences is whether you have true or false values following immediately afterwards or not. So if you've got an is error condition, and if it's not error, it jumps to afterwards, and if it is an error, it goes immediately following, versus the other way around, then those can have different performance impacts based on where the instructions lie in memory. And actually, sometimes when you're running a program in a JVM, you'll get different performance behavior separate times, simply because the instructions happen to fall out in a different way. Or if you recompile the program, they'll fall out in a different way. Or even things like, depending on the size of the environment variables you have with your program, then the data will be laid out in a different way. So if we had a cache line that looks something like this, then the layout on the right is going to work better, because the instructions that follow there's no error, the happy path, or immediately afterwards, they're more likely to be in the same cache line, and you can just push straight through. So even though the branch predictor might be 100% accurate, if you've already got the data in the cache line, then clearly it's going to be faster. And in C, there's a couple of built-ins expect. You can say, is it going to be true or is it going to be false? And you can hard code these things in. But again, these hard coding values often have plausible outcomes, and unless you measure the benefit and you're really getting down to the low levels, they're probably not worth it. It's much more important to have legible and maintainable code, for example. There's also something called the loop stream detector. So if you've got loops that jump up to the top for Intel processors, the loop stream detector kicks in when the start of the loop is at the beginning of a cache line. And there is a performance benefit or a performance notification that you can get if your loops fill in that and you're running on a processor that has that loop stream calculation. There are some flags if you're compiling things yourself. You can align all functions to a 5-bit 2 to the 5 boundary, and that will make sure that they fit on the functions. And you can align all the no fall through blocks as well, so that when you're not falling through things, you make sure they start on a boundary as well. That will take up more space in your instruction cache, and probably is only going to be beneficial either for some functions or for programs where you've determined that the looping and running out of cache lines is the issue. Now, there are some tools that will do these things for you automatically. Facebook had a incubating project called Bolt a few years ago, and on the left-hand side, there's a heat map of where the program counter was spending most of its time. The one on the right is exactly the same thing, but effectively they've defragged the memory hotspots in the running program. And as of a couple of weeks ago, I think November, Bolt has now been merged into mainline Clang, so you can actually run it with run it as a link time optimization or profile guided optimization step in there. There's another one called LVM Propeller. This was trying to do the same thing, where you would run your program, you would get a performance profile that happened, and you would then pass that performance profile into the optimized execution. And what it would do things like was take your functions, split them up so that each one lived in its own dot section within the assembly. And then when you enable those basic blocks, then the Clang compiler can orchestrate and move functions around in order to be able to give you the best performance in there. And so it's kind of like using thin LTO and profile guided optimization to be able to reduce the hot path of your program, again, in a similar way to Bolt. But that hasn't been updated in some time, and it's not clear whether or not the Bolt being merged into LLVM is where people are getting their effort behind for now. So something to watch out for. And then lastly, I mentioned converting to AVX. AVX is the single instruction multiple data set that allows you to do multiple data operations at one time. There's a JSON parser, SymD-JSON, which has now been incorporated in a number of different JSON parser libraries that uses AVX for being able to do its parsing. And you can actually get a non-trivial performance upgrade from being able to use that process, simply because you're taking in whole strings of data at a time rather than doing things character by character in order to be able to build up the content. So if your program is amenable to it, then moving over and being able to use single instruction multiple data and AVX operations is definitely a benefit that you can take advantage of. So to summarize what we've been talking about, for memory, when you store your programs and your data in memory, use cache line aware data structures, because that's going to be the single biggest performance benefit that you can get for the smallest amount of work that happens. You can, if you want to move faster than that, compress data in memory and decompress on the fly. There'll be less data for you to take up, there'll be less uses of the caches, and the CPU can operate much faster whilst waiting for things to come from disk. Avoid random access memory, and if you've got Linux systems, configuring them with HugePages can be a win. In fact, if you've got a desktop or a laptop, you might want to consider putting on compressed swap or compressed memory, because that in itself is another performance advantage, simply because you can decompress things faster than you can load them from disk. For the CPU, think of each CPU as its own networked mesh cluster, and each core will have its own communication system, and each socket will have its own communication system before it even gets out to the network card. And things like branch speculation and memory misses are the things where your program is spending most of its time. The majority of programs run from cache miss to cache miss. You can find out where that is by using some performance counters, either through JMH or Async Profiler or TopLev, or using some of those tools, and use auto vectorization. And that will give you the wider data structures and being able to operate things on more time. Now, as you might expect, there's a bunch of references inside here. Again, I will publish this presentation so that it's available to you. There's some links to various people's blog posts, forum groups, and other things which has been useful. And I'd just like to thank a bunch of people who made this possible, whether they knew about it or not, because I've learned from all of these guys. And I'd just like to call out again to Ken for organizing the Java Champions Conference, the other Java champions who've helped make this program possible, and of course, Java Juno, who's the Josh host who's been looking after me so well today. And with that, thank you very much. My contact details are here. You may take a screenshot of this one. I have uploaded this presentation to SpeakerDeck, so if you want to dive and get the presentation directly, you can. But if anyone has any questions, I'm more than happy to answer them now. Thank you very much.
Thank you, Alex. That was a great presentation. There were a couple of questions. I can go ahead and read them to you, and I will also put them on the screen just so you can answer. The first one was actually from Michael, and he asked, what are SKLs and cores? And Suboptimal then subsequently did answer that they're Skylake microarchitecture.
Yeah, so inside each of the chips, there's a different core that's inside. So whilst things might be called Skylake, then the core underneath has its own code name. So Willow Cove and Golden Cove are the cores that are being used in the new ones. Sunny Cove is what's used in the Ice Lake server processes at the moment. I can't remember what other coves that they had beforehand, or indeed the other lakes that they had beforehand. But each generation of processes is going to have a different core component underneath there. Wikipedia is actually pretty good. It's got a list of all of those core hierarchies, but also the link that I referenced for the different I forget where it was now. Let me just see if I can pull up the slide here, showing the different microarchitectures for the different cores has a pretty good overview of these ones. So this one that's created by Cardiac, that I've shown Sunny Cove, which is the Ice Lake one, and Golden Cove, which is going to be the Alder Lake / Sapphire Rapids one. But actually, he's got a whole bunch of, or she's got a whole bunch of these things for a number of different core architectures, both from Intel, AMD, Apple, and the high perf and low performance ones. But mostly when you see a diagram like that, things like ICL or IKL or GC or SC are to do with the individual core that's running inside that particular package.
Excellent, thank you. And then Takeshi had another question. How does TLB work when you have a supervisor plus virtual machines? And then also, does the supervisor emulate it for each VM?
That is a great question. So I think the right answer is that it probably depends, which I know is a real get out of jail card. Intel has got a variety of different hypervisor extensions that it uses to try and pass through as much of the content through to the underlying machine that runs, rather than needing to do everything itself. I don't know whether or not that's going to be exposed at that level and how that maps up. The thing is, the processor itself has only got one TLB inside there. And the hypervisor's job, even if what it's doing is it's allocating a subset of the physical RAM to one OS and a subset of the other physical RAM to the other OS, it's still going to be the same TLB that's being used to be able to process this. So I think you would find that even if you've got a hypervisor, it's not giving each OS its own TLB. It's a property of the virtual memory subsystem that the hypervisor is sitting on. And the OS is written in such a way to, instead of implementing and talking with its own processes, to then coordinate that with the hypervisor in an appropriate way. But I don't know exact details to give you the full answer of that. But my expectation would be that depending on how the hypervisor is configured, then it will handle these things for you. One thing, speaking of hypervisors, the AWS has got a whole bunch of Graviton 2 processes, and their hypervisors for EC2 over time have become more and more fully native, just passing things through. So I don't have the document to hand. I'll see if I can find out and then tweet out about it afterwards. But there is a view of how the hypervisors for Graviton have evolved over time, and how things have stopped being emulated in the OS and have moved down to a more native representation. So that's probably an interest. Might have the answer to some of those things.
Thank you. Perfect. And then Yoel had a question: is the JVM able to advise?
That is a great question. Thanks for that. There is a use HugePages or use transparent HugePages option within some of the more recent JVMs. I seem to remember that there were some changes about whether they were used or whether they were coming or whether they were automatically enabled. It's the same one with the use NUMA flag. So there used to be a use NUMA flag, which would allow you to say whether you wanted to enable NUMA specific optimizations. And there was the same one for the HugePages as well. But I can't remember if it was use HugePage or use transparent HugePage, or whether they were behind um, an extension flag or something that you had to use to unlock it.
Okay, thank you. And then Kirk had a question. Can you address loop alignment with the top of code cache? This was an important optimization we'd apply with a compiler directive on certain platforms. Would you say it still applies?
I would say it applies into the extent that, firstly, there are some additional hardware benefits for when your loop starts on the begin, or the target of your loop starts on the beginning of a cache line, which is the loop stream detector that we've already talked about. In terms of top of code versus bottom of code, actually, by the time your code is laid out and or loaded into memory, where that exists, whether it's on big numbers or small numbers, doesn't really make much of a difference. What does make a difference is whether or not they are, whether the hot functions are collapsed together. And what you can do in C-like compiled languages is you can mark sections of code as hot or cold, and then you can group all of the hot code together and you can group all of the cold code together. The reality is humans are not very good at doing that, at least not keeping it accurate over time. And that's what profile guided optimization is all about. So with profile guided optimization, you run your program with a set of expected data, and that expected data is then going to give you a kind of feel of how your program's going to work at runtime. And then that that organization is then going to be handled in the subsequent compile step with using the profiling data that you took before to kind of automatically collect together all of the hot functions. And that's a bit like what Bolt was doing in its the graphic that we showed later on. But actually, whether it's the top or the bottom, it isn't so important as much as whether they're all highly correlated together. Because on the left-hand page, on the left-hand image here, you're seeing your hot code distributed all over the memory, so it's pretty much in all of the pages of your instruction layout. Whereas on the right-hand side, maybe 5% of your instructions are hot, and they're all correlated into the 2 or 3 instruction pages, which means they're pretty much always going to be in the I cache or the ITLB cache.
Thank you. And I think we have one more question. Harish asks, typically, how many parallel issues does modern processors do?
Sorry, I'm not sure I understand the question. How many? What's the largest number of processors or cores that you have within modern systems? Was that the question?
Yes, how many parallel issues do modern processors have?
So the individual cores max out about the 40 line for Ice Lake. So there's an Ice Lake SP 40 core system, 40 core socket, which will have 40 cores on there. You can, of course, then have systems with multiple sockets on there. So if you had a 4 socket system, each socket containing 40 cores, then that would have 160 cores in there. You can go higher than that. I can't remember what the biggest machine that AWS sells, but certainly there, I think 1,000 cores is, or that order of magnitude is something that you could get today. Clearly, having lots of cores is very good when what you have is lots of computational problems to solve. If your problems are much more memory focused or memory bound or network bound, then having more cores is not necessarily going to make your machines run faster. And I think the other thing to realize with multiple cores is that when those cores are executing, they get hot and they need to be cooled down. And so even if logically you have a machine where all 40 cores can run at 5 gigahertz each, you probably can't run that for a sustained period of time without melting the chip. And so modern cores, both for power consumption and also for the cooling, will throttle down and do speed step technology to ratchet the voltage down to reduce the heat output and also to slow the machine down. So you probably don't get fast processing all the time. And if what you want to do is high performance all the time, then you probably want to disable the temperature step, and actually running on a socket with a smaller number of cores may give you a better total throughput. That's why in AWS, if you get a machine that has very high performance on it, it might have a smaller number of cores than something that's just going to be able to blat through batch processing in the shortest amount of time. By the way, I had a quick look at Java 11. There is a flag in there called huge TLBFS, which was one of the options of the table flag that I talked about earlier. That's on Java 11. I don't have Java 17 on the machine that I ran that, but I think there's probably a huge option inside there as well. You can find out what your JVM flags are by either using JMap and not JMap. What's the other one? The J thing. Too many commands that run with JCMD, that's it. You can either use JCMD to be able to talk to your VM and then be able to dump out the VM flags that it's actually running after it's done all of the argument parsing and processing and switching and so on. Or you can use -XX : plus print flags final, and then that will tell you the same thing, but at runtime. So if you want to find out all of the flags that exist that you can possibly tweak, then that's a good one to do. I will tweet out that so that people can find it afterwards.
Great info. Thank you. There was one more that just came in from Michael. He was asking, I have read modern CPUs combine CICSs and RISCs approaches internally. How does that work with Intel CPUs?
Okay, that's a great question. So what he's talking about is CICS versus RISC. So CICS is complex instruction sets, and CISC is complex instruction sets, and RISC is reduced instruction sets. The Intel ISA, the loads, pops, moves, and so on, was originally talked about in terms of a CISC instruction set. The reality is, whether or not you call the instruction architecture RISC or otherwise, when you get entries that come in and they are decoded and they then go into these micro operations, by the time you get to this stage, they're all micro ops anyway. And so those micro ops are effectively the RISC version. So you can think of Intel as being a CISC front end with a RISC micro op back end. But what the advantage that some of the ARM processors have being designed with this, first of all, is that they don't need as much of a frontline pipe because the instruction sets are laid out much more regularly, and therefore they can skip out a few steps. And if you skip out a few pipeline stages, then it means when you do have a processor bubble or a processor stall, there's less work to pick up and run for again. But realistically, I don't think people really worry about whether it's CISC or RISC anymore.
Excellent. I believe that's all the questions. Did have a couple of comments here from Kirk. He said that this was the flags, print flags final, and then also to look at the globals.hpp.
Thanks, Kirk. That's great. Saves me having to tweet it out. But as I said, if you want, you can download this deck from my speaker deck site. I'll tweet out a couple of the questions that I've remembered from this, but it sounds like Kirk's already done it for me. So once again, thank you to everyone who helped me make this presentation and who taught me what I know today. And thanks again, Josh, for hosting me, and Ken for making JChampions Conf happen.
No problem. Thank you so much. Great presentation.